Today what we're going to do is we're going to go into those standard normal curves. First, we're going to start out with just distributions, normal distributions for everyday things. In this particular lesson, the big focus is on birth weight for babies, and like all biological measurements, or at least most of them, they fall on a normal curve. So we're going to have to, if we're going to get proportions of babies at certain weight ranges, we're going to have to do some standardizing to make that work. All right, so we're going to do tables and we're going to do calculators. Calculators would be the preferred thing. Tables are a little bit old school. They're great when I was a kid and I was doing tables with logarithms, and I still remember those days with, well, something less than fondness. Well, anyway, so here in letter A, they say use table A, which is a standard normal table, Z table, to find the area or to look up the area to the left of Z equals negative 0.45 under the normal curve. All right, as far as tables go, these are available in your book. I think they're to the back. Now that makes it a little awkward since your book is electronic. So all you have to do is just go online and type into Google Z table PDF, and you're going to see probably one of your first links is going to be a download for the exact table I'm about to pull up. All right, so the best thing to do whenever we're doing one of these standard calculations is to just go ahead and produce a curve. All right, and I'll talk a little bit more about curves. So this is going to be standard normal curve, so it's centered at 0, and then negative 0.45, just guess at it, so negative 0.45, that would be this region right here. So they want us to find the area of that particular region. Now remember, the entire area is 1, so we're just going to get a straight proportion for it. So we're looking for the probability that Z will be less than, and you can do less than or equal to as well, it doesn't matter, you'll get the same answer, negative 0.45. Okay? All right, so it says to look it up in a table. Let's do it. All right, so if I can pull the table up here. All right, standard normal cumulative probability table. It's very common that these tables, in fact, all the ones I've ever seen, are going to be left tail probabilities. All right. Remember that this curve is asymptotic and it goes on forever in both directions. So if you want a lower limit for this, it's negative infinity. If you want an upper limit, it's going to be positive infinity. We'll talk a little bit about that. So anyway, looking at the table, you have your Z's going down this column. And the thing about it is Z-scores have decimals, and they're only 2 places. And so you can do more than that if you want to, but it is the accepted decision to have them to 2 decimal places. These are only listed to 1 decimal place. Here is your other decimal place. So we want negative 0.0, let me say it again, negative 0.45. So we can come down here, and we do have the negative 0.4. We just have to connect it to the 0.5 column, and we'll just go down, 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 and we're looking at this number right here. So that's it. The proportions or probabilities that we get are to 4 places. Z-scores are to 2 places. Now, the reason I'm emphasizing that is because it's accepted all throughout the field. So if you're taking an AP exam and you're trying to work with standard normal calculations, you get a Z-score that maybe is rounded to 4 or 5 places after the decimal, then your answer is going to be a little bit different from the answer choices that are going to be available, because those are based on 2 decimal points after 2 decimal places after the decimal point. it should be close enough for you to match them still. So I'm not too worried about that, but just FYI, 2 places for z-scores, 4 places for just about everything else. All right? So let's go ahead and put that down. What was that? I've already forgotten it. How's that? That's pretty bad. 0.3264. So let's get that recorded. 0.3264. Okay, so there you go. What else can I tell you about this curve? If you're interested in positive 0.45 or greater, that would just be a reflection of this grayed out area over here. And that's not going to be available in your table because it only goes from left to right, from negative infinity on up. So if you're starting from 0.45 and going up, you're not going to get it. But you can do negative 0.45. It's going to be the exact same proportion or probability because this is a symmetric curve. And if you want just to have this labeled and then this also labeled and find this clear area in between, then you can just do twice this area and subtract it from 1 and you'd get the area in between. Remember, I was saying if you had another one of these tails shaded in exactly like this, the area that wasn't shaded is just 1 minus the sum of the 2. All right, anyway, you can always use these tables for tests and quizzes. Some kids love them. You don't ever have to use it after seeing it right here. Because for us, what we're going to do is use the calculator. So we'll do, in the calculator, there'll be 2 commands we're interested in today. The first one is Normalcdf, and that just stands for normal cumulative density function. And what you want here is to go from the lower bound to the upper bound. Now the lower bound is essentially negative infinity. Your calculator has funny symbols for that, funny way of representing it. So I basically just replace any infinity with 1,000. So I'm just going to put negative 1,000. And what I'm saying is I'm starting this 1,000 standard deviations below the mean. I think that would be just about the same thing. In fact, you'll get the same answer as if you could put a negative infinity here. And then that goes up to negative 0.45. All right? So I'm going to assume everybody has an Nspire calculator. So looking at your Nspire calculator, okay, first of all, you don't need to open pages for simple calculations. You just get things too busy and it just gets, dangerous as far as maybe messing up. So I'm going to go into the scratch pad and I'm going to go into menu like I did for 1var stats, but I don't want stats. I don't want statistics. I want probability because we're working with probability models. Okay? So you want that, probability 5, then distributions 5, and in this final menu you want Normalcdf. Now we're also going to use inverse norm, which is in the same spot. So remember that when we get to it, it'll be after a while. So Normalcdf, all right, see how they represent that negative infinity? That's just kind of kooky, but that's what it is. Get used to seeing it. Positive infinity would just lose that negative sign. So keep it or replace it with negative 1,000, doesn't matter. And your upper bound was negative 0.45. You are in a standard model. See the 0 for the mean and the 1 for the standard deviation. So you only need to hit OK. There it is, 0.326. And if you round it, that will be 4. All right, so good deal. Let's go ahead and put that in here. So that'll be the exact same thing, 0.3264. Okay, so you have a choice. You can do tables, you can do your calculator. My guess is that you're going to do the calculator. Okay, so we're going to scoot down here. This blurb here is fine, but I think the notation is a little confusing. So scooting down here and avoiding the confusion, let's start looking at birth weight of babies in the United States. Like I said, most biological measures, it's modeled by a normal distribution. with a mean of 3,250 and a standard deviation of 550. So I'm just going to note that. This will be a capital N, parentheses, 2500 and 550. Okay, that's the shorthand notation. They're giving us a sketch of this normal distribution. It is not in z values. You can see that those are in the regular metric of the grams. And so we're just going to work off of this, but in order to cut it up, we're going to have to convert to z-scores. So it says up here that babies weighing less than 2,500 grams are considered to be of low birth weight. So that much or less is a low birth weight baby. So they want us to shade that region. All right. So I'm guessing that 2,500 is somewhere like, I don't know, maybe about here. So you go up and you shade it, do the best you can do. And then you have to guess at what the proportion of this entire thing is. Assuming that the area is 1, I would personally guess about 0.1 or maybe 0.15. It's awfully hard to guess these things right, and I know from experience that that's not super right. So let's go ahead and calculate the z-score for this so we can do some standard normal calculations. Now remember, z equals x minus mu divided by sigma. All right, so z here is going to be this particular x, 2,500, minus the mean, 3,250, divided by the standard deviation, which is 550. And if you do this in your calculator, this is going to give you negative 1.36. Yes. So remember 2 places, so I stayed with 2 places. And what we're seeing with this 2,500 is that value is at 1 1/3, 1.4-ish standard deviations below the mean. So these are that or less are low birth weight babies. All right, so I'm going to give this a pause because I need to switch my canvas here, my paper. So hold on. All right, so here we are, we're back, and that negative 1.36 z-score, they want us to look it up in table A. Okay, we can do that, but I'm going to put down kind of the notation for it. So this is like, it's asking for proportion. So if they ask for a proportion, or if they ask you to determine the probability, all right, don't give percent, right? It's going to be 4 decimal places of some number either at or below 1. If they want percent, fine, answer in percent, but answer however they ask. So this is the proportion or the probability of z being less than negative 1.36. And you can put less than or equal to because it really doesn't matter. You can just do whatever you want with that. So I'm going to just kind of pop up this table again, and we want negative 1.3 and then come over to 6, right? This is the 0.06, and so there it is. Negative 1.36 is right here. Whoops, I didn't mean for it to pick all of them. So 0.0869. 0.0869. All right, that was great. No problem. But it's very archaic to do that off of tables. I want to show you the flow of doing this using your calculator from beginning to end. And what we want to do is go from an x value to a z value and finally to a proportion or a probability. So we'll just start out with the original question was the probability that x is less than 2,500, low birth weight babies. That is going to be the same proportion as the probability that z is less than 2,500 minus 3,250, right? X minus mu over sigma. That's going to be 550. which if we shrink that down to a single number will be the probability that z is less than negative 1.36. We already knew that. We calculated it. Now it comes time to do this in a normal CDF. So normal CDF, and that's a left tail calculation, so it's negative infinity to this number. So I'm going to default to my negative 1,000 up to negative 1.36, and let's do that in the calculator. So here's our trusty calculator. All right, menu 5. We want normal CDF, and it's going to negative infinity, but just for grins, I'm going to change that to negative 1,000, just so you can see that it works. The upper bound was negative 1.36, and just tab down to OK. And there it is, 0.3264. I'll get it. So, here we go. Whoa, hang on, something's not right. Let me go back and see what happened. Oh, I used an earlier one. My bad, sorry. So let's go ahead and do it again. Hang in there with me. I've only done this 5 times today, and you can tell my voice is starting to go. So let's replace that with negative 1.36. Didn't I have that? Oh well, let's see. We should get the right answer now. Okay, 0.0869, just like we had before. All right, so let's go ahead and record that. 0.0869, maybe even box that in so your ancient teacher can find it. All right, that is a left tail calculation. We need to do a right tail calculation, and we need to do a central calculation that doesn't have a tail in it at all. So letter F, what proportion of babies would the normal model predict as having more than 10 pounds, 4,536 grams at birth? All right, so they drew us the same curve, and 4,536 is like way up here. It's this little sliver up in the right tail. So I'm thinking that my proportion is going to be pretty small, really small. Now, the one thing that I'm going to put a little asterisk on is this last sentence here. You should always start with a sketch of the area that you are looking for. This is very true. The AP graders and the AP people that write up the scoring guidelines love to see the curves. It is better than a verbal explanation. If you can label a curve correctly, then you're just telling them you know what you're doing. As far as the calculators speak, you know what? Let me change color here. Like this stuff here, the normal CDF, the AP people hate that. And I'm not even sure why they do, but they don't accept that. If you just put this down here and write an answer, they feel like you're missing something and they will not give you full credit. So beware. All right, so start with a sketch. When you look at what I uploaded for today's homework, I drew a sketch for just about everything. So let's go from X to Z to P for this one. So this is the probability or the proportion of values where X is greater than 4,536. That is the same as probability of Z being greater than 4,536 minus 3250 divided by 550. All right, now let's get it down to a single Z value. Well, we just need it to be a single number. So now Z will be greater than, and I'll do the work for you, 2.34. That means that this is actually at more than 2 standard deviations above the mean. That's why it's so tiny. All right? So this is going to go from this Z value to infinity, right? Lower bound, upper bound. So when we do a normal CDF to get our answer, we're going to be from 2.34 up to 1,000, or whatever you've discovered will work for infinity. And that's going to be a really tiny proportion of that curve, 0.0096. Yeah, not too many babies are born at that weight or higher. All right, so one other thing to show you that there's another option here, which I'm guessing most of you will probably opt out of. You can go at it a little bit backwards. You can do 1 minus the probability that z is less than or equal to whatever, 2.34. So you can find the clear part, subtract it from 1, and that'll give you that little sliver right there. Like I said, that's an option. It'll give you the exact same answer. All right, so left tail, right tail, now we got to get a value that's in between. All right, so they didn't sketch anything for us, so we are going to do the sketching. And we'll just do values before they're standardized. So remember, this is centered at 3250, and we want to go from 3,000 to 4,000. And you don't have to be super accurate with it, but it's going to be this region right here. And you can imagine that the proportion of babies between 3,000 and 4,000 grams at birth are going to be pretty big, because most of your area in these curves is to either side of the center. Okay? So the good news is that we know how to do this. The bad news is, yes, you're going to have to standardize two different things. So watch how I write it up. Starting with x, we'll say that 3,000 is less than x, which is less than 4,000. You can put equal to with it, doesn't really matter. So here goes. So that's the same as the probability of 3,000 minus 3250 over 550. That'll be less than whatever z is, which will be less than 4,000 minus 3250 divided by 550. Now both of those should shrink down to single numbers. So the left side is negative 0.45, and the right side is 1.36. So there are no infinities, be they positive or negative, that are involved here, because these tails here aren't part of your shaded region. So when you go to do Normalcdf, like so, the lower bound is negative 0.45, and your upper bound is 1.36. And you just put it in your calculator like that, and you get a fairly large proportion, 0.5867. So almost 60% of that curve is taken up with babies between those two weights. Pretty wild, huh? So letter H here just is going to ask us to compare real data with these models. Remember, the models are just, abstract models that don't actually exist in the real world. We just use them to make estimations or predictions or whatever. So here we have some actual statistics that were measured. You have 291,154 low birth weight babies out of a big total, 3,880,894. And if you shrink that down to just a proportion, you're going to get 0.0750. Now remember, up here in part E, we had 0.0869. So we have that as an estimate, 0.0869. And so that was our estimate, and they're pretty close. Pretty close. This is what we would expect. Now, to get between the 3,000 and the 4,000, we already have that estimate, so let's see what it is for real. That's 2,552,852, adjusted by the same total, 3,880,894. This will be a little different. This will be 0.6578. Remember, 4 places. And our estimate was 0.5867. So it's in the ballpark. It's not as good as what we had over here for the low birth weight babies, but this is what you run into with real data. It's unpredictable. We can get the best model we can and just work with it, and that's the beauty of statistics. You don't have to be 100% precise. Well, you can be real precise in your work, but your results may not match what actually happens. What do? Just go on. All right, now the last two things, I am going to put a star on this one, all right, because that means it's important. It's a different kind of thing. So when you read this, it says, how little would a baby have to weigh? All right, stop. If they're asking us how much a baby would weigh, our answer is in grams, right? So they're going to be among the lightest 2.5% of all newborns. That's a proportion or a probability or a percent. All right, so we're going from P, and then we're going to have to go back to Z, and finally to that X value, because how little would a baby have to weigh is an X value, okay? To be among the lightest 2.5% of all newborns. Okay. This is going to be, since we're going in the opposite direction of what we did in the previous parts, this is back standardizing. So let's put together a curve. And sorry about that, it's not super great. But if it's the lightest 2.5%, that puts that 2.5% down here, right? And we'll just go to 0.025. What we need is that z-score right on the boundary between the area that includes those newborns and the other side. All right, so we need to go from P to Z, and we're going to do that using our inverse normal. Inverse norm in the calculator, remember that? I said we were going to use it. It's great. All right, so it's under the same thing, 5, 5, and now this will be 3, inverse normal. Now, what inverse normal does, if I can just put this back up here, is it does those left tail probabilities, just like a z-table does. So from negative infinity to whatever the end is for your proportion that you're, or your probability that you're looking for, that will give you that z value at the very right side of that interval. Okay? So we're going to put 0.025. It's already set up for standard normal, so just hit OK. And that makes sense. It should be a negative value because you're to the left of the mean, negative 1.96. Remember, 2 places. So negative 1.96. And let's just write this out for notes. So this was inverse norm, 0.025. And that's where we got the negative 1.96. Oh, look, I'm getting mail. Thank you. Go away. All right, so remember we're using x minus mu over sigma equals z. Well, we know z, we know mu, we know sigma. We just have to solve for the x. So let's set it up. X is unknown, minus 3,250. It's the same mean we've been working on, over 550. That is going to be less than or equal to, and you can leave the equal to off, it really doesn't matter, negative 1.96. That's just basic math, basic algebra. So to undo this, you multiply each side by 550, and then you add 3250 over. And you're going to get x is less than or equal to 2,172. And this needs units because, you know, we lost the units here at the z-score. We need to put them back on. And if there's decimals beyond that, you can put the decimals on. That's perfectly fine. And so there it is. That's the back standardizing. So any baby at that weight or less will be among the lightest 2.5% of all newborns. Or at least that's what our model says. All right? So this next and last one is actually the same thing, but I'm going to put 3 stars on it because there's a little feature about it that makes kids miss it and go crazy. Now you want to know how much a baby would have to weigh to be among the heaviest 10% of all newborns. That is the other side of the curve, all right? So here's your curve. and the upper 10% would be here. So let's call that 0.1, okay? Color it in if you want. All right, so let's go ahead. We need the z-score here. All right, so that'll be inverse norm something. What is that something? Now, if you say 0.1, you've already lost the battle, all right? Because remember that this inverse norm goes from negative infinity up to whatever it ends at on the right. This is starting at the left and going to infinity. That's the wrong side. You can't put 0.1 here. Remember, 0.9 is below that. That is what you need, okay? Let me just illustrate this in the calculator because it's really important. So menu 553. All right, let's just say you make the mistake of putting 0.1 in there. Okay, kids, do that. And you hit OK. See how you get negative 1.28? That is not on the right side of the curve, folks. That's on the left side of the curve. If you use that number, you're going to get a value that represents like the lightest 10% of the babies, that much or less. You don't want that. You're going to get an answer that's actually below your mean when you need something that's way above your mean. Now, what you can do if you make this mistake and catch it is you can take that negative sign off, because if you actually do it the correct way, all right, menu 5, oops, naturally, let's try it again. Menu 553, and you put in the 0.9, you should get the same number without the negative. So it is 1.28. That makes sense because you're like a standard deviation above the mean. So 1.28. So if you get a negative, catch that. If you don't catch it, your answer will be less than your mean. Then you should see that. If you just let it go, you're just not watching. All right, so again, we're looking for an x value, minus 3250 divided by 550. This time it's got to be greater than, I'm just going to leave the equal off. Forget the equal. We'll get rid of that. All right, 1.28. And so multiply by 550, add 3250, you should get x is greater than 3,954 grams. That makes sense because your mean is 3,250. This needs to be bigger than that. All right, so there it is. It's really important that you learn this stuff, and hopefully this helped you. I have the homework key posted. I've gone to great pains to make sure it's accurate with all the curves drawn. So have at it. We're going to be working on this Friday and into Monday. So if you feel like you're not clear on things, ask. We're going to get free time to do it. So I'm going to suspend my efforts, and I will see you soon.